Okay, so we have shown that if you fixed a strictly positive real number t and a non-negative integer n, then the probability that exactly n calls arrive up to time t is given by this particular number, in the e power minus alpha t into alpha t whole power n divided by n factorial. In order to write the summary slightly differently, we'll define for each non-negative real number t our new random variable nt to be the number of phone calls that arrive up to time t. In other words, nt is a maximum n such that Sn is less than or equal to t. Okay? That's the number of phone calls that arrive up to time t for every t bigger than or equal to 0. Of course, this will immediately tell you that, first of all, you're taking a maximum, so that set has to be non-empty. So this set is indeed non-empty because S0 is equal to 0. So for every t bigger than or equal to 0, this set is non-empty because n equal to 0 is always there in that set. So there is no problem. Also, S1 is strictly positive with probability 1. S1 taking the value 0 is 0. So therefore, it follows that N0 has to be 0 with probability 1. Okay. If you put t equal to 0, this set is going to be just, with probability 1, this set is going to be n equal to 0 because S1 cannot be 0. And therefore, S1 can be 0 only with probability 0. So therefore, this maximum is going to be U0. Okay. So we have just shown the following result, which follows directly from the equation last time I had written. For each t non-negative, NP, there is apparently no reason why this maximum should be finite. It's a set of non-negative integers. It's a subset of non-negative integers on which you're taking the maximum. But we have actually shown that it is indeed finite with probability 1. More precisely, we are given the distribution of nt. You have shown that n0, okay, we have just shown here that n0 is 0 with probability 1. By the way, whenever a random variable is degenerate and 0 with probability, we degenerate at some constant, we'll just write it like this. We'll write this to mean that n0 is 0 with probability 1. This is our notation. Yeah, we had used it earlier also, and we'll follow that notation. It's quite standard. For t equal to 0, then nt, which is n0, is basically 0 with probability 1. For other t's, namely for any t positive, nt is just Poisson with parameter alpha t. Okay, for all t. In particular, expectation of nt is going to be alpha times t. And this is true for all t bigger than or equal to 0. Actually. Okay, so let's prove this proposition. So recall that nt from the previous slide is the number of phone calls that arrive up to time t for any t non-negative. Okay, and which is basically the maximum of all n bigger than or equal to 0, so that Sn is less than or equal to t. And for each t bigger than or equal to 0, we'll first show that nt is finite with probability 1, and we'll show also that for t positive, nt would be Poisson with parameter alpha t. In particular, this will show that the expectation has to be alpha t. So expected number of phone calls up to time t is alpha times t. Okay? So expected number of phone calls up to time t is proportional to t. And the constant of proportionality is this alpha. Okay. So we already have shown that n0 equal to 0 with probability 1. So therefore, we know that n0 is finite with probability 1. n0 is 0 in fact. So therefore, it has to be finite. So therefore, it's enough to show this for t strictly positive. So let's assume t is strictly positive from now and fix such a t. Now, we'll use the calculation that we have done to show that nt is finite with probability 1. So nt is finite is same as saying NT takes, by the way, NT is a non-negative integer value random variable. Okay, NT can be a non-negative integer only. So therefore, NT finite is same as asking NT takes a non-negative integer value, which is the sum of NT equal to n, where n runs over all non-negative integers. We have computed the form of probability of NT equal to n. And that's just e power minus alpha t into alpha t power n by n factorial. If you sum this over all possible values of in 0 to infinity, this will give you 1. This is because this will come out and this sum is exactly e power alpha t. Okay. So therefore, this is this guy and this sum is just e power alpha t, which is 1, which gives you 1 after multiplication. So therefore, we get that NT is finite with probability 1, which was not at all clear a priori. Okay. Because it's just a maximum which is over a possibly unbounded set. But it won't be unbounded with probability 1. That's what this is saying. Okay. So on the other hand, NT follows Poisson alpha t because we have already computed this guy. And this is true for every t positive and all non-negative integer. So therefore, we have actually shown that this is Poisson with parameter alpha t, and therefore, the expected number of phone calls up to time t has to be equal to alpha t. There is no other choice. And this equation is true for all t actually bigger than or equal to 0. Of course, it's true for t positive, strictly positive, because of Poisson with parameter alpha t has mean alpha t. Even for t equal to 0, n0 is 0, therefore expectation of n0 is also 0. So therefore, this is true for all t non-negative. Okay, so we have defined this stochastic process NT, which is the number of phone calls up to time t. This stochastic process is a continuous parameter stochastic process because the index set here is the set of all non-negative real numbers. This continuous parameter stochastic process defined here is called a homogeneous Poisson process on the positive real line with intensity or rate alpha. Now alpha is the parameter coming from the underlying exponential distribution. Okay? And it's a strictly positive parameter. And everything is happening on the positive real line, so that's why we call it a Poisson process on positive real line. And why homogeneous, that will be clear later. Okay? So we'll see that. We'll talk about this later. So many times we'll just drop the word homogeneous and also we'll drop the phrase on 0 infinity. We'll just say NT is a Poisson process to mean NT is a homogeneous Poisson process on positive. Okay. So this is clearly a continuous time stochastic process. It actually counts the number of arrivals of phone calls up to time t. It's what is called a counting process. Okay. So it counts the number of phone calls up to time t when inter-arrival times are IIT exponential random variables with parameter alpha, which is strictly positive. Now, why homogeneous? As I said, this will become clear later in the course. There is also something called inhomogeneous Poisson process on 0 infinity, or more generally on other spaces, not just 0 infinity. But this will be beyond the scope of this course. We're not going to discuss such things. Inhomogeneous Poisson process on 0 infinity we'll touch upon once, but we won't analyze it in details like the homogeneous case. Okay, so how does the NT look? Let's try to look at that. So NT looks like this. So it starts at 0. So N0 is 0, remember? So by the way, here I put the 0 here just so that the graph looks nice. So this is a graph of T versus NT. So on the horizontal axis, I have T. On the vertical axis, I have NT. But this is not the origin. The origin is here. This is T equal to 0 as well as NT equal to 0. So at T equal to 0, NT is equal to 0. So therefore, the graph starts at 0, 0, 0. This is the origin. And then it remains at 0 until the first arrival occurs. The first arrival occurs at the time S1. At the time S1, it jumps to 1. And then it remains at 1 until the second arrival happens, which is S2. At the time S2, it jumps to 2. and stays there till the third arrival happens, when it jumps to 3, and so on. So this is the shape of NT. So in other words, NT is a right, as you can see, NT is a right continuous function. The only discontinuity is from the left. Okay. So it's a right continuous step function that starts at 0 and makes jumps of size 1 with discontinuity from the left exactly at the arrival times, namely S1, S2, S3, and so on. Now, these arrival times are, of course, random variables, right? So, therefore, this is actually a random step function. It's a random function, and the randomness comes in the positions of the jumps. Okay, everything else is deterministic. Okay, it's the only positions of the jumps are random. Okay, so more precisely, if you look at the graph, you'll be able to read off that NT takes the value 0 as long as T is bigger than or equal to S0, which is 0, and strictly less than S1. NT takes the value 1 as long as T is bigger than or equal to S1, but strictly less than S2. NT takes the value 2 when T is bigger than or equal to S2 and strictly less than S3, and so on. So in other words, whenever T is between Sn and Sn plus 1 with, well, Sn I'm allowing the equality, Sn plus 1 I'm not, then NT takes the value n. This is how the NT looks. Okay, so this brings us to the end of the first lecture. I hope everything was clear. If not, please, I encourage you to do that actually. Please feel free to drop me an email that this part wasn't clear, and I'll try to explain it to you over email. If not, I have your phone numbers as well, so I may also call you if I think that email is not enough for explanation. And of course, please revise all the materials that we are going to need from Probability Theory 1 and 2. It's going to be absolutely essential. Okay, so then I'll see you on Friday in that case. So, bye.